Hi, and welcome to the talk on our paper, Simple Techniques Work Surprisingly Well for Neural Network Test Prioritization and Active Learning. This paper is a replicability study. If we talk about deep neural network-based systems, or in general systems driven by some AI component, we can observe what's called the virtuous circle of AI, meaning as the system gets deployed to many customers, it actually can track the production inputs of those customers, which is more data, which then can be used to test and retrain the model, leading to a better model, hence better predictions, hence a better system, which again attracts more users, right? So essentially, we have kind of this self-supporting circle, which allows to build a deep neural network-based system as we collect more data to become ever better. However, there's of course some limit to that. If we assume the system has millions of users and each of those millions of users produces thousands of data points or even more every day, we can't just collect all these data points and use them as test data or to retrain our model. That would just be too much. So what we need when we track production inputs is we need to select the relevant production inputs for our objectives, which are testing and retraining the model. And hence, what we do is we employ a so-called acquisition function, where from all the data which passes through our user systems, we select which ones are actually useful or relevant for testing and retraining. To that extent, I think 2 years ago at ISTA, a paper was proposed called Deep Genie, where they proposed to use the Gini impurity for classification problems to collect samples which can be used to identify DNN faults, hence samples which lead to a misclassification, or to select samples to retrain the model, so-called active learning. This Deep Genie approach, which is not the first one with these objectives, has very important advantages. Mainly, it is extremely fast. It works just on the softmax output, which we get when we do a prediction anyways. And it doesn't need any special collection of training time artifacts. It's also has been shown to outperform alternatives from the literature. So it was a quite convincing paper, which also by now is I think had quite a little bit of impact already in the literature. So we perform an empirical study to replicate the findings in the Deep Genie paper. And to that extent, I'm going to first show a bit our design choices. So this is a bit of an overview of the original study by Feng and his colleagues. So that's the Deep Genie paper. The paper shows 3 objectives. First, the test prioritization. So the goal is to highly prioritize misclassified inputs. Then on active learning, where we want to select some additional training data to improve the performance. The idea here is that we have a fixed percentage of inputs that we can select, and of course, selected these subset, this limited set of additional inputs, the accuracy of the model should increase as much as possible. And then we also wanted it to be very fast. They assessed their proposition by the means of 4 different case studies. So MNIST, Cypher10, Fashion MNIST, and SVHN. However, MNIST was used only for only MNIST was used for test prioritization. The other 3 data sets were used for active learning together with MNIST. Then as baseline, they used a selection of different neuron surprise coverages from the literature. And as test sets, they used both the nominal test sets from those data sets as well as adversarially this test set under an adversarial attack, so adversarial inputs. We changed this a bit just to take into account some threats to validity and hopefully make the experimentation generalize a bit better. So at first, we performed the full experiments on all case studies and all test sets, where they used the selection for reasons of time, I assume. We perform all experiments on all case studies and all test sets. Then we include more baselines. So first of all, we include naive baselines from the uncertainty literature. That's, for example, just the vanilla softmax, so the highest predicted softmax probability, for example, or Monte Carlo dropout as another instance that we took from uncertainty literature. And we also included novel variants of surprise adequacy. So the original authors, they just tested surprise coverage, which is based on surprise adequacy. We also directly use surprise adequacy and include new propositions of variants of surprise adequacy to do so. And then to make sure that our results are not susceptible to random influences during training, so random initialization of model weights, for example, we run every experiment 100 times and then aggregate the results to account for these random influences. Then next, we diversify the case studies. So where the original study used 4 image classification, 4 small image classification data sets, we replaced one of those data sets with a text classification data set, just to give the evaluation a bit more diversity. And then we replaced the adversarial inputs with corrupted inputs, realistically corrupted inputs. So this has been something we've seen in recent literature, is that adversarial inputs, while being very useful in triggering a misclassification, they are very unrealistic in most real life scenarios. However, corrupted or commonplace corrupted inputs is a kind of a novel way to lead to a potential misclassification, where we say we corrupt the input in a way as it could happen in the real world. So we see here 2 examples from the literature where the image here is blurred, which can happen. This one here is, I think, a PNG to JPEG and back kind of translation loss. So for those 2 data sets, we could use what's proposed in the literature. And then we proposed similar corruptions for Fashion MNIST and IMDb data set. Good. So now, equipped with this, we can dive into the results. And of course, with everything I mentioned before, there's many results. These are the tables from the paper, and even those are only a subset of the results, with the rest available in the replication package. And just going over them now, we don't have the time, and it will probably not be a very entertaining talk. So we'll just look at the main conclusions. And the main conclusion is, and that's most importantly, we successfully replicated the main findings of the original paper. So Deep Genie is, of course, orders of magnitude faster. We also showed that analytically, but it also outperforms surprise coverage and neuron coverages, all the ones we tested, in the vast majority of cases for all case studies. So that's definitely a successful replication, despite us using a different experimental setup. So that's, I think, a very confirming finding of the original paper. But then we find that the other simple approaches that we included, so that's the softmax-based ones, like just vanilla softmax, where we take the predicted probability, which isn't a good probability estimate, but it's occurring a very good test prioritizer and very good guidance of active learning. And we found that such a naive baseline as vanilla softmax performs equally well as Deep Genie. We performed a statistical analysis, and when comparing those 2, there's a very small effect size and no statistical significance, which is surprising because vanilla softmax, much before Deep Genie, was known as kind of a go-to baseline in uncertainty quantification, which is a very related question. Here, however, we want to mention that this doesn't necessarily mean that all approaches are bad. This means that we use APFD specifically to test test prioritization, which is a standard metric. Similar metrics have been used also in previous papers before Deep Genie, and it lacks to capture a lot of objectives that I think we should have in test prioritization, such as collecting a diverse test set. At the moment, every misclassification, every input leading to misclassification is counted as a unique DNN fault, whereas clearly in practice, as many inputs are probably very similar, I'm not sure whether that makes a lot of sense. So for example, diversity should be an additional objective, and then I'm not so sure whether those simple approaches, including Deep Genie, would still outperform other approaches. And then on surprise adequacy, where we also did a vast range, we were actually also able to make some observation. And those are again replicating papers from surprise adequacy. So first we find that surprise adequacy reliably outperforms neuron coverage. We found that Mahalanobis-based, so that's kind of the most recent version of surprise adequacy. Mahalanobis-based surprise adequacy is a very good replacement for likelihood-based surprise adequacy, leading in general to similar results, but being orders of magnitude faster. And then lastly, we find, again, consistent with existing literature, that DSA is the best of all surprise adequacy, but it's slow and it works only for classification. And this also emphasizes the strength of, for example, Mahalanobis-based surprise adequacy, as this one we can use for regression problems. Deep Genie, Vanilla Softmax, the other simple baselines we used, they only apply to classification problems. If you want to generalize this to regression problems, we need to use, or I would propose now, based on these findings, to use Mahalanobis-based surprise adequacy. Good. So if that gets you a bit interested, if you want to look more into this, we release a wide range of artifacts. So first of all, much of the large experimental suite we implemented think could be useful in other contexts, but then you don't want to take our huge experiments and extract just the important classes. So we did that for you. And we released 3 Python packages or data sets. First of all, the test prioritizers as a pip package, a text corruptor, which allows you to generate realistic corruptions of text data sets, and then similarly a precompiled data set for the corrupted fashion images. Our paper is available on arXiv. The link is also on the conference page. And if you want to replicate our exact results, there's a Docker package. There's all the artifacts available online on Zenodo. The artifact evaluation committee was able to successfully replicate all results. So that's quite a finding we're happy about. Good. So summarized, we performed very extensive experiments regarding test prioritization and active learning. We successfully replicated the main results from the Deep Genie paper. We hence show that Deep Genie shows the best results, but also on par with Vanilla, Softmax, and other simple baselines. And we release a wide range of versatile artifacts, hoping that they facilitate future research on this topic. Thanks a lot.